Any questions?
When is the midterm?
Say again?
Did you mention the midterm?
Yeah, so the midterm I just announced on the Slack and also on the website. So the midterm will be happening. Let's go to the. Yeah, so you can see it will be released on the morning of 8th October. All the dates are on the website or on the Slack channel Thursday. So it will be released Thursday morning and it will be due Monday morning. It will be an exam that I would have normally given in 2 hours because I have taught this class in the past, so I know what is a reasonable exam length for 2 hours. And but you will have as much time as you wish to take to solve it. There is no time restriction. You can use the internet, you can use books, your notes, calculator, Mathematica, Python, whatever you want to do, you can do. The only thing that is, however, not allowed is discussion between you and your classmates, between you and your parents. I don't know why you would like to discuss thermodynamics with your parents, but maybe you do, but you cannot do that. You cannot go and ask on the forums. You can go and look up things on the internet. I mean, many of these, there are lots of internet forums where thermodynamics problems are already discussed. If you want to go and browse through those things, it's all fine. But you should not be engaging in a discussion about all these things. And we have a sense of figuring out when two people have discussed, we have taught enough classes and we get a sense for that. Please don't do that. You have lots of time. Just try to do your best job yourself. And you can do it in as many sittings as you wish, even though it's 2 hours, you can take more than 2 hours. If you want further clarification on grading on the homework answers to homework questions, do we need to come to office hours or will a solution set be released? The solution set is already online on the website. Typically, I will be releasing solution sets or keys the same time as you get back your graded answer. So for this one, the set is already online. If you still have questions, please send a direct message to Connor, although I must say that he has been quite generous in giving grades. So in general, it's not a good idea to, I mean, it's a good idea, of course, to get feedback on what you could have done better, but trying to argue over marks typically ends up not becoming productive, because what happens is that Connor might realize, hey, wait, why did I give you extra points in this problem? And he's allowed to do that. So, but please refer to the solutions. They are already posted online. Yeah, so the midterm, since it's a take-home midterm, it will be of its, I'm not going to ask you to just write down things verbatim. All the problems will involve some amount of thinking, and hopefully you will enjoy it. And Friday, again, Friday, Rebecca Black is stuck in my head. On that Friday, 9th of October, there won't be any class. So you have at least 1 hour from that class that you can take to do the midterm, and you can find 1 hour elsewhere. And yeah, any questions about this? Will the difficulty of the midterm be significantly higher than the homework? Yes, it will be higher. For sure. It's an exam, it's not a homework. There's a bit of a difference. It counts for more and it will be a bit harder. All right. And you can ask me more questions on the Slack. There will be one more homework before that. So you will get more chance to practice, and all of this material will be included in the first midterm. Okay. So let's resume where we started. Let's resume where we stopped last time. We were starting to think about the change in internal energy for a generic real gas for non-ideal systems. How does it work? So we know for an ideal gas, this is simply number of degrees of freedom multiplied by RT by 2. And many of you keep asking me questions about whether this is per mole or per molecule. This is all about the units that you have decided to use. So in any problem, we will be very clear as to what you have to use. You won't have to worry about this in any problem. But for a non-ideal, so this is simply a function of temperature. There is nothing that goes on over here. So partial U by partial P or partial U by partial V is equal to 0 for ideal gas. There is no dependence on a volume or pressure. But for a generic gas or material, this is not going to be the case. Will all the midterms be the same format given a few days to do it? I cannot promise that. The second midterm, depending on how you all do in this one, the second midterm might be a project that you work on in teams and read through papers. It's likely, but I cannot promise. That last time, that's what I did. And I'm interested in doing that, but it depends on how everyone does in the midterms. If everyone does quite well, then it's likely it will be a project. But if I find that people really need to churn through problems, then it will be a traditional midterm. The final, and same thing applies for the final. So I cannot make any promises, but there is a chance it will be, it's not guaranteed that it's not guaranteed anyway right now, but you will be given a notice of, just like this time, you know, at least 2-3 weeks before the exam as to what will be the format. So for the second midterm, I will tell you right after grading the first midterms as to what is the format. Great. So we want to figure out how does this U change with pressure and volume for generic non-ideal gases. How do we do that? In order to do that, we will focus on a closed system. We could generalize it to open systems also, but we will just look at a closed system of constant composition.
I think your screen is frozen.
That's annoying. So we will look at a closed system where matter is not being exchanged between the systems and the surroundings. What does that mean? That means that the variable n can be treated as a constant. It's something that is not going to vary. So we don't need to worry about n. So in this case, U is going to be a function of T, V, and P, right? It's going to be a function of pressure, volume, and temperature. Now we know in general, if n was to vary, then we could have written pressure as a function of volume, temperature, and number, right? Or volume as a function of temperature, pressure, and number. But since n is a constant, we can say pressure is a function of volume and temperature, or volume is a function of temperature and pressure, or temperature is a function of pressure and volume, right? So this thing can easily be written as U as a function of, for example, if we choose to write volume as a function of temperature and pressure, this could have been written as temperature, volume, and pressure, which is now, so we are going for this one, for example, which is a function of volume and temperature. We could be written as that. So what does that mean? If you really think of it as in terms of a function, this is now U as a function of temperature and volume. Why is this a correct operation? Because this pressure now depends only on volume and temperature. So we put in temperature and volume in there, and there is nothing else. Or we could have written it as U as a function of temperature, volume as a function of pressure and temperature, and pressure. In this case, U would be written as a function of temperature and pressure, because there is no explicit V here. Whatever V we had is now expressed as a function of pressure and temperature. So what's the summary of this operation? It means that the internal energy for a closed system of constant composition can be written as U as a function of temperature, volume, U as a function of temperature, pressure, U as a function of volume, pressure, right? Either of these three works. What turns out to be simplest, and there is a deeper reason for why this is the way we work with it, which we'll revisit after second law, so before second midterm, is that this representation is the most useful. Thinking about U as a function of, I don't know if you can hear frantic running in the background. That's Pahora running, trying to save us from some postman. So we are going to think of U as a function of temperature and volume. And we know U is a state function, so we can think about its exact differential. What would be the exact differential? That would be du. And now that can be written as partial U by partial temperature at constant volume multiplied by dt plus partial u plus by partial volume. So those of you who went through the module on dependent variables would realize that is what we are doing here, right? That whole business, which might have seemed arcane to you, it's already become useful here because you were given u as a function of tvp. And now for this one, we have decided to consider p as the dependent variable. And what does that mean? That means we have eliminated p from the perspective that we are doing here, that we have here, and just we are left with t and volume. We could have done the same thing if we eliminated in this one over here, we eliminated v, and we could have gone with a different framework. But as you can see, the answers will be completely different. What we are doing right now is completely dependent on the fact that we eliminated p. So this is why that module was important. But as you work through this, you will see there was nothing really very abstract about it. Hopefully you will see that. So now we have these things. This one we have already seen before in the last class. Partial u by partial t at constant volume is nothing but the heat capacity at constant volume, right? Try to recall. du is equal to dq plus dw is equal to dq minus pdv if we are looking at only expansion work. And at constant volume, this thing is 0. So du is equal to dq. Therefore, Cv, which is dq by dt at constant volume, is equal to partial u by partial t at constant volume. This is just to refresh your memory from last time. This was the definition of Cv. So here we have Cv dt given this derivation plus partial u by partial v at constant t multiplied by dv. So Cv dt we have seen before. This other thing we haven't seen. This other thing also has a name. It is called the internal pressure of the gas or of the material. And sometimes it is denoted just as P, but in order to avoid confusion with the actual external pressure, the variable that we use also for external pressure, we are going to call it as pi T. Pi as in everyone's favorite symbol pi. And there is a constant temperature here, so we have put in T. So what does this mean? This, look at it from an intuitive perspective. You have a system which has a certain internal energy U. Now you are changing the volume of this system, but keeping the temperature constant. So you have a box and you measure the internal energy of the molecules in this box. Now you expand the box and you measure the internal energy of the volume of this box. And this process is done isothermally. As you do this, the system is coupled to a heat bath, which makes sure that the system stays in equilibrium thermally. And there is no mass transfer going on anyway. So you do this process isothermally, staying at equilibrium, and you measure how the internal energy is changing. If it was an ideal gas, we know that U is equal to, I'm just going to write nRT by 2, even though it's n degree of freedom, right? Therefore, partial U by partial V at constant T is equal to 0. So for an ideal gas, this internal pressure is 0 for ideal gas. But for a non-ideal gas, it is going to be different. So before we get into how it looks like for a non-ideal gas, we can write down the total derivative of du now. So du is therefore given by this term, pi t multiplied by dv plus cv multiplied by dt. So here what we have done is to think about change in u for constant composition, treating P as a dependent variable. In a lecture or two, we will derive the same thing. When we don't treat P as a dependent variable, we treat something else as a dependent variable, and then we see what goes on. Okay, so
What does that say at the bottom? Changing U for constant composition?
yeah, changing U for constant composition, treating pressure P, sorry about that, as a dependent variable. Okay, I will pause just for a bit over here so you can see what we have written. We are starting to get into calculus land a bit more heavily now. Any questions about any of this?
The overarching like du is equal to pi of t dv and everything, that equation, that's for non-ideal and ideal.
Oh yeah, this is for everything. This equation is so powerful, you can apply it to the universe. You can apply it to a black hole, you can apply it to the ocean, you can apply it to a protein, absolutely anything. This is very true, very, very generic. So one of the things I used to love when I was teaching PChem in a classroom was to give pop quizzes. So today I'm going to give you a pop quiz right now. This pop quiz will not count towards your grading. It's fully anonymous. So I'm not even going to judge you as to what you have done, but I would like to see how you all are doing. Okay, so this pop quiz is going to have 3 questions and you have 3 minutes to answer this question. So I'm going to release it in a, all right, let's release it. Do you all see it? Cool, so there are 3 questions, they are multiple choice and work through them. Halfway done, 1.5 minutes left. Twenty seconds left. Again, it's anonymous, so don't worry too much. Just do your best. Okay, 10 seconds bonus time. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, -1, -2, -3. Now we have to stop. Pakora is in the house. Hey, Pakora, look, those are your fans. Hello. Oh. Yeah, he went for a walk in the rain, so he's a bit wet. Can you post questions to Slack later? Yes, I will. Good. All right. So do you all see the poll results? 89% of you got the first problem right. Again, the idea is quite simple. I'm very glad no one got W square right, because that is dimensionally incorrect. The other things can be confusing. And if you got it right, don't beat yourself. If you got it wrong, don't beat yourself up. Just try to remember the concept for future. This is one of the most important things that you're learning in this class, is that if you have a system and you give a certain amount of heat to the system Q, and you do a certain amount of work on the system W, the net effect on the system is the same. It's going to increase its internal energy. It will change by U. So if Q is positive, W is positive, it will lead to a certain amount of change in U. If they are negative, then U will go down. But the system itself cannot tell whether it was heat or work done. This one is slightly, we did it last time, it's slightly more subtle than the first problem. And 75% of you got it right, which is that the expansion has to be reversible. In general, reversible work, and for this, please go back to my lecture notes from last time, or the video from last time, where we drew the pressure volume curve. And we had one in which the pressure was decreasing like a hyperbola. And we said the area under the curve is higher than the area under the curve if you directly brought it to the final pressure. And if this is completely wrong, if you got this, you should really think, why did you think this way? When the system is contracting, you're not getting any work out of the system. You're doing work on the system contracted. This one is something we haven't really gone in this class in detail, but this is something you should have done in GenChem, the question between the difference between extensive and intensive quantities. Again, happy to see that the highest winners, not winners is a very bad term, the number of people who got the maximum same answer is actually correct. It's this one. Pressure is intensive. Volume on its own is extensive, because if you double the mass of the system, the volume goes up. But volume divided by mass, which is density, is intensive. Temperature is intensive. Here, pressure is intensive, but volume multiplied by mass, that's like double intensive. That's intensive squared. Internal energy is intensive. So this one, please go and refresh your intensive and extensive properties. This is something I have found people forget all the times, even in the graduate thermodynamics and statistical mechanics class. I give the same question on the first pop quiz, and believe it or not, even graduate students, you guys actually did better overall in the performance I have seen in the graduate students. People forget about intensive and extensive, and this is actually quite basic thing that you should try to remember. So good job, you could do better. And these pop quizzes, again, are not to judge you in any way. I don't even know who voted what. I am not going to grade you on this. This is purely for your feedback. And yes, I will post the questions online. Okay, good. So now let's go back to I was going to give a pop quiz last time, and what happened, I was sitting in the wrong Zoom room. So I was so sad. When no one showed up at 9 a.m., I was like, okay, it's terrible. I realized I was in the wrong Zoom room. Okay, great. Cool. So we have just written down that du is equal to pi t dv plus cv dt. And I mentioned that for an ideal gas, we have been talking about this, u is a function only of temperature. There is no pressure and volume dependence. And this is something we keep using again and again. It's not obvious. It really followed from the kinetic theory of gases. So please go back and refresh it. In your brains, there should be a chain of logic, so you know that this is obvious. When you look at it, you should be like, I know where that comes from. I see this, we go from here to here to here, and that's how it comes from. That's the type of reasoning you should have in your head. So for a perfect gas, why is it really independent of volume? Intuitively, the reason is that the internal energy only depends on temperature. What does this mean, that the internal energy depends only on temperature? It means that the only contribution to the internal energy, there are two ways a material can contribute to the internal energy. It can come from potential energy, or it can come from kinetic energy, right? An ideal gas is one where the potential energy is 0. And the only contribution comes from the kinetic energy. Why is the potential energy 0? Remember the U versus R curve that you drew, I think you're drawing in the second homework? That's the whole idea there. For a Lennard-Jones or for a real gas, you have a U versus R, which looks non-trivial. It has a minima, and then it goes out to 0. For an ideal gas, it's boring. If you come too close, it goes to infinity, otherwise it is 0. So there is no potential energy, there is only kinetic energy. And if you have only kinetic energy, it does not depend on volume. It does not depend on volume. Kinetic energy depends only on temperature. And this is the reason for a perfect gas, U is proportional to T. And we also saw it through equipartition. Equipartition allowed us to basically put in the proportionality constant over here. So what does this mean? This means partial U by partial V at constant T is equal to 0. For a non-ideal gas, this is not going to be the case. For a non-ideal gas, it's going to look typically, it can be complicated. I'm going to draw two generic examples. So for an ideal gas, there is no interaction between the molecules, right? They do not talk to each other. Therefore, an ideal gas, it looks like this. For real material, so again, I did not mark the x's, terrible. U versus volume V. We are talking about internal energy. And again, remember always, this is something that used to confuse me when I was a student. Internal energy is not the same as potential energy. It is the sum of potential energy plus kinetic energy. So thank you all for helping each other with handwriting. It simplifies my life. But what condition makes potential energy 0? Potential energy comes from the interaction between molecules. Potential energy is 0 because in an ideal gas has no interactions. That's why it is 0. Yeah. So for a generic gas, it can look one of two ways. It can look either like this, or it can look like this. Did I freeze?
Yeah, frozen.
Oh, terrible. It must be so annoying for you all. I would have just connected it with a cable, but Apple, and it's true Apple style, requires me to go and buy like separate dongles just for doing that. And I guess I'll have to do that. Okay, so for a generic gas, it will look either like this curve or like this curve. It could be a combination of both also. It might increase first and then decrease later and things like that. We will just work on these two cases. What does this one mean? This one means that as the volume is increasing, the internal energy is decreasing, right? So in this one, partial U by partial volume at constant temperature is negative, while in this one, partial U by partial volume at constant temperature is positive. In other words, the internal pressure in this one is negative and the internal pressure in this one is positive. So I want you to think now, if repulsive forces, so these two cases happen, one of them happens for repulsive forces and the other one happens for attractive forces, for example. So what it means that ideal gas has no forces, right? Molecules don't repel each other, molecules don't attract each other. If a material has repulsive forces dominated, for example, Coulombic interactions at small distances try to repel each other, right? So it depends on the distance between things. But in general, if you have repulsive forces dominating, for example, hydrophobic attractions, where certain proteins, certain residues in proteins don't like to hang out around water molecules. If you have taken any biochem or even gen chem, you might recall that sometimes in proteins, the hydrophobic residues are buried inside the protein core, right? Because they hate water so much. So if repulsive forces dominate, then as you increase the volume of the system, it says, I like this, I'm happier. And when you are happier, what happens to you? Your internal energy goes down. When I say gas, we are referring to a generic system. So I keep saying gas, but it is some generic system. So if repulsive forces dominate, as you increase the volume of the system, it takes a sigh of relief. It goes, I hated you, and now we can have really a lot of separation between each other because I don't want to be next to you. So the internal energy goes down. But if attractive forces were dominating in the system, as you increase the volume of the system, it goes like, hey, wait, why are you pulling me away from this friend of mine? You know, I want to hang out closer. And the internal energy goes up. In other words, for attractive forces, as you decrease the volume of the system, the internal energy gradually goes down. The system becomes happier, or the gas becomes happier. It's like, yeah, I like it. Let's hang out closer and closer. That's the idea. Of course, if you go too far close, you can imagine this thing starts to blow up again, but you know, we are just talking about rough behavior. So this already shows you why this framework might be so useful. I hope it shows you, because you could perform a heat capacity experiment on a system. You could assume some internal energy model. If you could measure this internal energy as a function of volume at constant temperature and see how it looks like, you can go and judge whether your material is made up of repulsive forces or is it that attractive forces are dominating. You can go and learn something about that goes on into the system. So in the remaining few lectures, we are going to do a lot of manipulations of partial derivatives. Sometimes when you look at the notes, it looks like, wait, is this chemistry or did I just run into a math class? You know, this is just math. On one, there is nothing like chemistry if you really think about it. But that is the same as saying, looking at a sheet of music and saying, there is no music here. These are just some hieroglyphics, right? That's not the whole idea. You have to be able to learn that, and then you can see the music that is in there. So this is almost like music in a certain way. And just like I could never go beyond beginning guitar because I was terrible at reading the sheet music. If you don't enjoy reading these type of expressions and manipulations, you will have a hard time in thermodynamics. So it's important that you become comfortable with these manipulations, because as we defined in the first class, thermodynamics is about change in energy. How can we control it? When is it possible? Things like that. And change means calculus. And we don't have just one variable, we have many variables. So it's change of many variables, hence partial derivatives. So, okay, so this is what we got. All of this was what we got from thinking of the internal energy as a function of temperature and volume. We are going to come back in next class to think about, we are not stopping today, we are going to do other things. In next class, we are going to think about what happens to internal energy with respect to temperature at constant pressure and things like that. For that, the only difference will be that we will think of it, we will just play around with our partial derivatives and we can derive those properties too. In the remaining part of this class, we are going to think about something else. So there is a question which is, does the internal energy go up for attractive because potential energy is increasing due to increase in their potential to do if work is released, or is it due to both KE and PE? You can just think of it as potential energy. You don't have to even invoke kinetic energy for this. Kinetic energy does not really depend on volume. And any change that is happening due to volume at constant temperature, in fact, has nothing to do with kinetic energy. In classical mechanics and statistical mechanics, this is called as the Hamiltonian being separable. The temperature part goes only to kinetic energy, and the volume part goes only to potential energy. So it's coming only from potential energy. What I want to do now is to think about we saw so far that, let's see, where's my thing? My screen froze again, that's so annoying. We looked at the change, the amount of heat required to increase the temperature of a system if the process was being carried out at constant volume. And we saw that in this case, so the next topic is enthalpy. And let's see why we need this concept of enthalpy. So far we saw that du is equal to dq plus dw expansion plus additional dw that we are not considering about. So if plus dw additional, we did not really take that into account for now. It's just add. I'm even not going to write it because we are not simply considering it. So if dw expansion is equal to 0, which is constant volume process, that is constant volume, then we saw that du is equal to this thing. This is very interesting because this tells us that if you're doing a process at constant volume, the change in heat that you need to do, the amount of heat that you need to add to the system, even though heat itself is a path function, the amount of heat that you need to add to the system becomes the difference of a state function, right? Here we are saying that the change in a path function is the same as the change in a state function. And that's kind of profound statement. It's really nice, right? That this could happen. But this happened only at constant volume. So a natural question to ask is, what about instead of constant volume? So doing things at constant volume in reality is actually quite hard. Why? Because you have a box, and in order to maintain constant volume as a process is going on, you will have to keep increasing the pressure a lot, right? If the volume is trying to expand, you will have to gradually keep increase the pressure so that it does not expand. And if the volume is trying to contract, you will have to decrease pressure. And low pressure experiments are hard. Manipulating pressure, if you have ever done any experiments, you can imagine changing the pressure involves moving lots of pistons, this and that, it's hard. What's more natural in an experimental setting is to let the volume change and instead work in a constant pressure setting, where you say, I don't care, I'm just going to let it happen, for example, in atmospheric pressure. I don't care about how the volume is changing. Instead, I want to make sure that the pressure is constant. So what does this mean? We are looking at, we had this system which was made up of gas, and we gave some heat into the system. Heat was given in to this. And we saw that at constant volume, the amount of heat you gave, delta Q, was equal to the change in delta U, the internal energy of the system. Constant volume means that this thing was not allowed to move, right? Now, instead, let's imagine that we have a piston connected here that can move up and down. This thing can move up and down. And as you are giving heat to the system, you are doing it at constant pressure. So as you give heat to the system, what will happen? The molecules go, oh, we got a lot of heat, right? And they start bombarding against the walls harder and harder, right? And we know that bombardment against the walls is basically pressure. So the pressure goes up. But you have a little piston over here that can move up and down to release this pressure. So for example, in this case, we are talking about heat given to the system. So in this case, the gas wanted to expand. And now it can do that because the piston simply moves up. So this thing will gradually move up to this position. So the question we ask now, that in this case, can we find a state function so that the delta Q is now the delta in that state function? It's not going to be the internal energy now. That should be obvious. Why should that be obvious? I say obvious sometimes like a mathematician, because even if it's not obvious, I mean, you can work through the logic and see that it follows. The reason why it's not obvious is because now this term, the reason why it's obvious is because this term, the dW expansion, is no longer zero, right? The gas is now actually expanding against the piston that you had on top of it. So in this case, delta Q is not going to be delta of U. it's going to be delta of something. So our first question is there even a state function that can be put in here? Turns out, yes, there is a state function, and it is called enthalpy. And we will show that this enthalpy is given by U plus pressure volume. And the reason why this happens is because when you are doing a process at constant volume and you give some heat to the system, all of it goes into increasing the thermal energy of the system, right? They just start to wiggle faster and faster. So everything goes into the change of the internal energy of the system. But if you are giving the same heat to the system at constant pressure, the system now also expands and does work against this pressure that was being applied from outside, right? So not all of the heat that was given to the system is going into only increasing the internal energy of the system. Some of it is lost in doing work against that force that the system was expanding. So, and we will just show that indeed delta Q is equal to delta H for this function enthalpy. Even before we go there, I want to make a point that this is a state function. These two are also state functions. Therefore, H is a state function. So in some books, you will find this distinction calling, no, U is a state function, pressure is a variable of state. It's a kind of a bad distinction. Those people did not really take the fun with function modules, because you can always move things around. There is no such subtle difference between a variable of state and a function of state. You can move them around. So H is a state function. I think it was Maggie who was sharing her list of state functions yesterday, so you can add this to your list. This is a new one that we have now, H. So let's see that indeed, let's try to prove this, that indeed delta H is equal to delta Q for constant pressure. We have already seen that delta U is equal to delta Q for constant volume process, right? This we have already seen. Now we are going to see the second one. How to do that? So for this, let's look at the differential form. So let's write down the proof. Differential form dH is equal to d of U plus pressure times volume, right? Because H is defined as U plus pressure times volume. That is du plus pdv plus vdp, right? I took d of pv and used the product rule. But we are doing constant pressure process. Is equal to 0 at constant P, right? There is no change in dP. So we have now dH is equal to du plus pdv. Now we can use first law of thermodynamics, and you just did it in the pop quiz. du is equal to dq plus dw. If there is no additional work, that is dq minus pdv plus pdv, right? So du is replaced, and my u and v sometimes kind of look similar. I should work on that. So du is dq minus pdv, but now this minus pdv and plus pdv cancel out, and we are left with dq at constant p. So we just showed that change in a state function, again, a nice exact differential, is the same as the change in a path function if the process is carried out at constant pressure. So, and this brings us to the concept of heat capacity at constant pressure. So we saw earlier that heat capacity at constant volume is partial U by, what is the definition of heat capacity at constant volume? That the exact definition is change in dq, this horrible path function, by changing dt at constant volume. And we saw that at constant volume, this numerator is a nice thing. It is du by dt. We should write partial, sorry, because we are keeping things constant. So this is partial u by partial t at partial volume. This we saw last time. And today we just saw that similarly Cp, which is the heat capacity of the system. Now you're asking, how much heat will I have to give to the system to increase its temperature by dt if the process was being carried out at constant pressure. So this will be partial H by partial T at constant pressure. And this constant thing is very important. Can anyone try to reason with me if Cp will be more than Cv or Cp will be less than Cv, or can we say nothing at all? So this is quite easy if you think about this model. You gave some heat to the system at constant volume. The system can't do anything. It's trapped at that constant volume. So all the heat goes into increasing the temperature of the system. In other words, you are not losing any of the heat. You're making maximum use of the heat in order to increase the temperature of the system. However, if it was a constant pressure process and you allowed the system to go up and down, some of this heat that you gave to the system will be lost in moving, in doing work against the surroundings. So not all of the heat is going to increase the temperature of the system. In other words, the amount of heat that you need to give to a system to increase its temperature by a certain amount is higher for a constant pressure process. And I'm saying this towards the end of the class. For any of you who is watching the video later, I want to emphasize this is a super important discussion that I just had in the last 1 minute, and I'm going to repeat it. If you give heat to a system at constant volume, everything goes into increasing the temperature of this thing. But if you give heat to a system at constant pressure, some of it goes into doing work against the atmosphere, right? So you don't get as much bang for your buck, so to say. Some of it is lost in doing work against the system. Therefore, Cp is always higher than Cv through this argument. And my screen froze, which is terrible. So because when you do a process at constant pressure, you always lose some of the heat in trying to do work against the system. Therefore, Cp is more than Cv. Next class, we will derive a very simple relation, and I want you all to go and try to do it on your own. And please post the solution on Slack so others can see it. I will still go through the derivation, but I want you to think about it. For an ideal gas, Cp minus Cv is equal to Nr. We will show this. And your hint here is that partial U by partial V at constant T is equal to partial U by partial. No, I'm not going to give you a hint. Go and think about it. It's not too hard. If I give you the hint, it makes it type 1 fun. I want you to think through it. So this is true only for ideal gases. Later through the course of this semester, we will derive some very, very generic relations which are actually true for non-ideal gases. So in reality, for any material, there is a beautiful relation which goes as follows. Alpha square multiplied by temperature multiplied by volume divided by kappa times kappa subscript T. This is true for any gas. Absolutely any material that you can imagine will have this true, where this is coefficient of thermal expansion. And this is called compressibility. And this is a super generic relation. However, we will be able to do this after the second law of thermodynamics. And this is absolutely true in general. And this is true only for ideal gas. And I want you to think about this when you have time as to how to derive this. You should be able to do that. Okay, so see you in next class. There is a question on chat. It's kappa T, kappa subscript T. It's not Boltzmann constant. It's not Boltzmann constant. And also don't worry about it right now. What the point here was, you will be able to derive relations like this, which are absolutely true in general for anything, not an ideal gas, but a black hole, a white dwarf, a sun, a protein, a battery material, all of them follow this relation, Cp minus Cv. And that's wonderful, because if you do an experiment where you measure Cp and you want to figure out, well, what's going to be the heat capacity for this material at constant volume? you can go and back calculate it just by using this expression. For an ideal gas, the simple thing is true, and you should go derive. Okay, great. See you on Monday.